We're going to be talking about the topic of supercharging science, how organizations can drive innovation with AI. It'll be moderated by Jennifer Glore, Senior Director of Customer Engineering at SambaNova System.
First of all, thank you so much for having us. And I wanted to introduce my two panelists. I have Venkat and Kunle joining me. Would you guys please introduce yourself? Venkat, let's start with you.
Yeah, thanks, Jennifer. I'm excited to be here. I'm Vishwanath from the Argonne National Laboratory. Argonne National Laboratory is a Department of Energy national lab, and I'm a computer scientist here at the Argonne Leadership Computing Facility. And I work with data-centric applications spanning material science, cosmology, neuroscience, to scale their data-centric needs on large-scale supercomputers. And one of my key areas that I focus is on how to enable AI for science. And thanks again for having me.
Thanks, Venkat. How about you, Kunle? If you could introduce yourself, please.
Sure. So very glad to be here, and thank you for inviting me to this session. So I'm Kunle Olukotun, and I'm a professor at Stanford, where I've been there for many years. I'm also the co-founder of SambaNova Systems and the chief technologist. And my focus is high-performance computing of all sorts, thinking about how to do computing all the way from what programming languages and applications to develop to cutting edge compiler technology to the new hardware that will drive performance for future AI and science applications. And so I think about the vertical stack, and this informs both the research that I do at Stanford and also a lot of the cutting edge technology that we're developing at SambaNova Systems.
Great. So let me start it off with just a more general question. From your perspectives, what do you see as the biggest challenge to deploying and scaling AI applications? Kunle, let's start with you.
Well, I think, what you see in AI applications, no matter what area you look at, if you look at science and research, or if you look at commercial enterprise deployments of AI, it's all about increasing the capability and accuracy of the models. And that is driven by size and complexity. So what you're seeing is a huge increase in the size and complexity of the models that one wants to build in order to do things that are much better. For instance, if you look at natural language processing, GPT-3, which is a model from OpenAI, has 175 billion parameters, right? More than 10 times bigger than the previous big models. And so what one needs then is an infrastructure that is both very high performance to train and to serve these large models, but also is very flexible, right? Because the sorts of things that you want to do are not fixed. It's large parameter models. Today, it may be something that it involves processing of images or dealing with different kinds of data tomorrow. And so what you want is a flexible capability to handle the complex models, but then you also want scale, right? And so you want high performance because, of course, you want to train in reasonable amounts of time. You want to be able to deal with the complexity, but you want to be able to scale to these huge models that will give you the state-of-the-art accuracy. And so bringing these all together in a usable, easy-to-use environment is kind of the key to managing and deploying scale, AI at scale.
Yeah, and I think that makes sense. We're certainly seeing, as you mentioned, the scale challenge with NLP and vision recommendation and science, of course. And I know we're working with you on that, Venkat. So why don't you give us, your thoughts on the biggest challenges you're facing at Argonne?
Oh yeah, I'm happy to do that. And Kunle really pointed out some of the key challenges in the size and complexity. When we deal with science applications, we deal with various different kinds of features. It could have structured data, unstructured data, combination of text, images, categorical data, numerical data. We deal with streaming data as well as data sets that we generate from. The sources could be simulations, could be large-scale experiments that we do. So from a very wide, diverse set of fields. Just to give you an example, if you think about connectomics, where we want to map out the human brain and really understand some of the connectivity that we have, this really helps in understanding either neuroanatomy, or if we want to understand diseases such as Alzheimer's, the understanding the structures is very key. If you take into account the way we do it today, we segment and we slice these brain tissues that we have, and each of these slices that we get in today's technology could be in the order of 80K by 25K images, and you could get maybe 25K of these. This is today's challenge to tackle maybe a 1 millimeter cube image. We want to scale that out to say a 1 centimeter cube image. And if you want to do a human brain, that's significant orders of magnitude larger. So this is just one aspect of the kind of scales that we really need to solve to really understand complex phenomena. And this is the kind of applications where AI is helping us better understand some of these nuances that is kind of exploring this unknown space here.
Yeah, that's actually a great segue. So I know in some of the work that we're doing, and with your traditional supercomputing deployments, you guys are exploring new architectures to reach the scale that you need with some of these new explorations in science. And so, what does that vision look like from an Argonne perspective?
Yeah, so our traditional supercomputers are exceedingly good at solving, PDE equations and things that we are key in a wide variety of scientific domains. And this will continue on. I think this is still one of the key workloads to get, to enable scientific discovery. Together with this, with the ability to capture more data from sensors, to integrate data that we get from experiments, to improve our models that we have, or in some cases we are really not aware of models, and we need data-driven models to augment our existing models. We see a very wide set of new use cases that will run on future supercomputers. So, something that we have to consider is, how do you architect systems that will accommodate existing traditional supercomputing applications, these new novel AI for science applications that are becoming more production ready on these big systems? What is the infrastructure that is needed to enable these? If we have to develop ways to communicate between these two, what kind of communication channels will be have to architect? How do you even program these systems? The programming models, runtimes that are needed to enable this end-to-end workflow. These are the kind of challenges that we need to consider for this design space of future systems here.
Yeah, well, and certainly, I think ease of use, how quickly people can start using the technology, how quickly the existing workloads and new things can come over is key. So Kunle, I know you've spent so much time looking at, what are the attributes of a next generation AI solution and what that should look like. It would be good if we just got your input there.
Yeah, well, Venkat lays out the challenges very well as to sort of, what the future of AI and science is going to be. It's going to be about, combining traditional modeling and simulation with AI models, right? That can, in certain regimes, scale the performance of the simulation by orders of magnitude. But what does that mean? Well, that means that you need to be able to use the simulation data from the traditional modeling and simulation to train AI models, and you may need to do that on the fly, right? And so there's this notion that you can have training completely separated from inference goes away, right? You now need to bring training and inference together onto the same platform, and that needs to be closely coupled to the engine that's generating traditional simulation data, and could in fact be the same environment. The other, overarching issue is, of course, that if you look at the driver to performance in the computer industry, Moore's law, that's slowing down, right? And so traditional ways of doing computation based on instruction set processors, CPUs, or even more specialized processors like GPUs aren't scaling in the way that we want to keep the performance improvements that we've become accustomed to going. And so what you need then is something that handles all of these different disparate issues, and yet, brings in this point that you just made about being easy to use and being programmable and being flexible. How do you bring this all together? And so this is a lot of the things that we've been thinking about, at Stanford and SambaNova, and the conclusions that we come to are, that a lot of the application drivers are moving to what people have called domain-specific languages, right? So they are, in the ML arena, it's a language, environments like PyTorch and TensorFlow. In other scientific domains, it could be specialized languages. But what that means is that what you get as a systems implementer, as a systems designer, is a higher level of abstraction of the application. And so then it's the key challenge is to take that description, which tends to look like some sort of data flow description, and map that very efficiently down to execution. So that's what we've been thinking about, how to come up with this hierarchical data flow representation and how to optimize that. And then, of course, support terabytes sized data sets for models and simulation, support the sorts of things that you need for current and future generation AI models, like sparsity, right? So it's not just dense matrix multiply, it's sparse graph-based models. It's sparsity because you want to be able to deal with complex data that may have various different communications. It requires that you can handle, potentially even data processing, because you need to accelerate everything. We just said, conventional CPU performance is stagnated, so everything now has to be accelerated. That includes traditional data processing that you might need for doing the data preparation. And so bringing these things all together in a single unified architecture is ideally what we need for the next generation AI solution.
And I think, obviously there's alignment between SambaNova and Argonne, and we've been exploring different use cases with you for a period of time, Venkat, which we appreciate. And I think the audience, would like to hear, regardless of whether they're in the science space or not, what you guys have been able to do with our platform. We know that we've been spending a lot of time with you on vision and other areas as well. And we've allowed you to sort of explore new areas of science and see some results that you haven't been able to see before. So I think it would be good if you spent some time walking the audience through some of the things that you've been able to accomplish so they can get a feel for the work that's being done.
Indeed, happy to do that. And we've been using the system to understand the impact that we can have for a diverse set of applications. the applications that we have evaluated span trying to understand, better understand how treatments for cancer. So in this case, we are understanding what kind of combinations of doses can be used to either shrink a tumor, so will it have an additive effect, or will it actually prove to have more adverse reactions? So that's just one example in cancer research that we're looking at. We have examples that we have been investigating in neutrino physics. And in this case, we are looking at really large-scale images that we get from detectors. And this is very common in imaging experiments that we see across the complex over here, as well as kind of the imaging data that you get from various sensors. So in the neutrino physics experiment, we worked on together on a model called Cosmic Tagger, which uses a U-rested architecture, which is, and the goal is to look at kind of detecting cosmic backgrounds in this liquid argon projecting chamber. So it's a kind of a typical image classification problem where the goal is to say, are these cosmic images, backgrounds, is it muons? And one of the interesting aspects of this is that the data sets are very sparse as well. That's one. And the data sizes that we get looking at the detectors, today we are looking at 1280 by 2048. And these are the smaller images of what we believe we can look at today. The actual experiments will be at least orders of magnitude larger data sets is what we can acquire. So that's the kind of goal that we're looking at in the 50K by 50K going ahead in the future. So even with the data sets that we get today, they really don't fit on the systems that we have evaluated in the hardware accelerators, such as the GPUs. And we've been able to take and run these on in the native resolution on the SambaNova system, and able to achieve close to state-of-the-art training accuracy, which is really impressive scientific results beyond what we have achieved with the downsampled results. And it just paints a picture of the trajectory that we want to go. Right now it's 2K by 1K, and it gives us the opportunity to say, if we have to move towards the 50K by 50K sized images, the path and trajectories and the challenges that we have to face to do it. So that's just another example.
Yeah. And that's a great example, because for us, I know Kunle was talking about models getting bigger and image sizes is getting bigger, right? And what was high resolution a few years ago is standard or low res today. And our platform, because of the way it's architected with the large memory configuration, as you know, Venkat, we can go to 50K by 50K or larger. And so we look forward, to going on that journey with you. And we really see you sort of as the front of the pack in innovating in the image space, which will touch public sector and commercial technology innovation as well. Are there any other use cases you'd like to touch on before we move to the next question?
So this is just one example, right? So we have similar use cases where we're looking at, a recent more example is trying to understand the therapeutics for COVID-19, where we run several large-scale MD simulations and are using this to train and better understand the conformational space for protein-protein interactions. And protein-protein interactions is, again, depending upon the size of the system, you could either map it as a contact matrix, which is a 2D image. You could look at a graph representation of it, which is, I would say, the direction that you actually want to go to. And the kind of systems that we look today are in the 100K to a few millions. The size of the systems that we want to go are, again, in the 100 million to a billion atoms is where we want to achieve. And again, this is yet another example of the scale of the systems that we can go to better design therapeutics for, say, either for cancer research, for COVID-19 research, or a wide variety of other sciences. So, we're definitely looking forward to pushing the limits in terms of model sizes, complexities, and scale over here.
Yep. No,
yeah,
that's
just
great,
to follow up there, Venkat makes the case so clearly for why we need this huge model capability, and yet, in order to achieve and provide the sorts of capabilities that the SambaNova system achieves, it takes deep thinking about how you design a system that can both provide high capacity and high performance at the same time, right? So you look at conventional systems and they give you very high performance, but with low capacity memory, right? And so in order to understand how you build a system so that it gives you the scalability in terms of memory size with the performance that you got with the small memory, that is where the cleverness comes into. And that is the key to thinking about how data moves and how data moves efficiently, and don't move it if you don't have to, right? And then, so once you think about that data flow, then you get into a system that can be optimized both for high performance and high memory capacity. And so that's kind of key to the SambaNova system and why it's able to do so well on these large, high resolution, or even what we call in true resolution, right? So the resolution on your cell phone cannot be handled by conventional 3K by 4K, right? That's the size images that most mobile phones take, but they cannot be handled by conventional accelerated technology. And so we can do that because we have an efficient way of dealing with memory and dealing with high capacity image models and other models.
Yep. So Kunle, I know Venkat, referred to some of the use cases we're working on with Argonne on, and so I don't know if you have any, other use cases you'd like to mention or talk about, and how SambaNova plays as models get bigger and more complex.
Yeah, I mean, we're working. You got one area, of course, is high resolution imaging, but the other area, the other couple of areas that we're looking at are in the natural language processing area, and we're looking at sort of how to do very large models like GPT-2 and GPT-3. 13 billion parameters, 175 billion parameter models, and training those, to state-of-the-art accuracy with performance that beats existing accelerated technology. So that's another use case. The other use case that we're looking at are in the recommender area. And again, this all comes down to being able to deal with very, very large tables that basically represent user preferences. They're called embedding tables. They give a notion sort of, what you like to do when you browse around the internet, whether you like, or what sorts of movies you like to look at in order to make good recommendations, or as to what products you should buy, or make good recommendations for movies. The better representation that one has of your preferences, the better that you can make these recommendations. And so that leads to large embedding tables. And so being able to handle these large tables means we can get state-of-the-art accuracy on these deep learning recommendation models. And not only can we do it really well for what's called large batch training, but when it comes to inference, we're like 20 times better than existing accelerated technology, again, because we efficiently move data using this data flow representation and technology that we have.
Great. Thanks, Kunle. Now, back to you, Venkat. So with your experiences at Argonne and pushing sort of the boundaries of what's possible with AI and an accelerator like SambaNova, what challenges have you uncovered, and how do you see simplifying this moving forward? Some people might appreciate, some thoughts here as they go on their own AI journey.
Oh, definitely. I'm sure we can spend hours together discussing this. As we embrace AI for science, some of the challenges that we face in general is the types of data that we see are very complex. In many cases, the models or the data sets both are very sparse. Dealing with extremely high dimensionality is another big challenge that we've seen. Another interesting thing that we see in this space is large-scale hyperparameter optimization as well as network architecture search are key workloads that we have to see. We see network architecture search as being another useful use case for science where you could seed a network and now start searching the network space itself on what might benefit scientific use cases. And again, like Kunle mentioned about NLP, this is an excellent example. We have large number of scientific journals and publications that capture this very critical knowledge about what has worked in the past, what has not worked. And there's exciting work going on to use NLP to mine this literature for science. And now if you start combining that together with tasks that are dealing with images, so you can think about in the cancer use case where you have health records data together with CT scans, and building models that combine these together are some challenging areas that we have to explore and go towards. We already talked about how do you program the AI for science going forward on these big machines, and that's a key aspect for us to investigate and explore. So it's exciting and fun times, and a great area to be, living and dreaming.
Yep. And so, I know in the work with you and with others, there will always be folks like Argonne who are pushing the boundaries and developing new models and new research capabilities and bridging, science and AI. There's also, how does AI become more accessible for the masses, right? Not everyone has a large-scale supercomputer like Argonne or other places around the world, as well as the, esteemed team of data scientists that you and others have. And so, one of the things that we at SambaNova are trying to do is bringing AI to the larger community. We have something called Data Flow as a Service, which is more enabling customers right out of the box to get solutions, pre-built and bringing data so they can implement AI quickly. That's one of the things that we're working on. But Kunle, as we look to end this session in under a minute, what else do you think is needed to get AI to the masses, and how does SambaNova help with that?
Well, I think you hit it on the nail on the head. What you need is to accelerate time to value, right? So that for for the enterprise, they want to embed AI in their business processes, and so SambaNova has to we are figuring out sort of what exactly is needed for different business verticals, be it financial services, healthcare, oil and gas, and provide those solutions that have worked for our lighthouse customers to a more variety of customers in those particular vertical spaces. And so that's the key thing. So how do we provide time to value? How do we bring these AI models to help them improve their business processes?
Okay. Yeah, I think that makes sense. I will pause. I know I'm not sure if there's any questions yet, but we can keep going for a few more minutes if there's not. I will point out, I know some of you are in person and some of you are virtual. For those of you that are in person, there may be a couple locations. We do at SambaNova have someone in the Leiterman building in the patio area. Chris Kenny, he's the head of our European business development and international team. He's happy to chat with anyone after the fact. So if you're there, you can say hi to Chris. Hopefully he's making himself known to those in that area. Any last closing comments that you want to share with folks, Venkat?
I'd say it's an exciting time to be applying AI in science, bridging both traditional modeling and simulations with AI techniques. This is exciting in terms of new science. It's exciting in terms of new technologies and new. It's going to open the doors in various new scientific discoveries. So it's a great time to be in science.
So I guess there is one question so far from the audience, and it's, I used to help on research categorizing phenomenon and spiral galaxies using Hubble space technology. And how does AI drive discovery in that area? I don't know, Venkat or Kunle, if you have any thoughts.
Sounds like one for Venkat.
Sure.
Maybe more so.
This is a fantastic question. And recently we've been looking at trying to do galaxy classification, and this is a great. Looking at examples from telescope data sets as well as other detectors. One of the simplest ways to say, looking at the shapes and say whether it's a spiral galaxy or it's a spherical galaxy, and they have different connotations over here. And we've actually applied something very similar to that. You can make that into a image classification task at the simplest way. So getting data from all the telescopes, you could start looking at various objects that you can detect, and next classify them as what kind of objects these are. This is one of the examples that we've actually run on the SambaNova system as well. So this is just one example of of approaches that we can take here.
Yeah, and I think what we're finding is,
just to add to that, these telescopes are getting bigger and bigger in terms of their resolution, right? And so we want to enable these classification problems to be done at full resolution without having to downsample, and that way you get the highest classification accuracy possible, right? And so that's, from a systems point of view, it's, hey, how can we make this doable at the highest resolution that's coming off the telescope? Yeah, and I'll also add that in addition to this, you get data sets of different modalities here. And looking at microwaves or infrared, among others, and combining them together to really solve this problem is kind of a key next step that several groups are working towards.
Yeah, I think one of the things we see was, as we work across industries and problem sets, many of these problems that used to be solved in other ways can use and benefit from AI. And so obviously different industries and different problems are at different stages, but it's going to be very exciting to see how the technology is used to solve problems across a variety of spaces. Kunle, any closing thoughts from you? Yeah,
I mean, it's clear that AI is continuing to transform the world. And what we want is to make this transformation process, as painless as it could be, by providing the kinds of capabilities to scientists, to researchers, to people in the business enterprise that can really accelerate the use of AI technology by both providing the use cases, the models, and the underlying systems that can power this transformation.
Great. I think there's one more question that just came in. Are there still any bottlenecks in semiconductor industry that more funding can unlock? Maybe Kunle, that one's for you.
There's still well, I mean, at the moment we're undergoing a semiconductor shortage, but the problem with semiconductors is that it takes years and billions of dollars to develop new fabs. So this is not a quick fix. One has to have a long range view about where the global semiconductor industry is moving, but it's clearly a place that semiconductor companies need to invest. Potentially, the federal governments need to invest also.
Yep, that makes sense. So Venkat and Kunle, I wanted to thank you for your time. Thank you for all the audience members for attending and the good questions that we got.